Cat, and today I'm going to teach you this is a tutorial on how to run QSM analysis in order to obtain QSM maps. And I'm going to use data that I've downloaded with DCMconf command from HPHI. I'm going to process all the data on HPHI as well. And this data was downloaded from the Webix server, and I've just used the DCM command, and I've downloaded QSM related data, so it's magnitude, T2 star, and I've downloaded in DICOM format, as you can see here, and I've downloaded the phase as well, which comes with it. This is very important because you have to use the phase. The phase is the primary thing to calculate QSM maps, and these two datasets go hand in hand, and you can use the DCM2NI command to convert these to knitting. This is what I usually do. So then I get magnitude raw, which if I open it, you can see what it contains and also the phase. In terms of the magnitude, you can see that there are various images. So it's a 4D volume in which in each volume there is one echo. So if I go further, you can see that the image gets darker because as the echo times get longer, the images get darker, or the signal decreases. And in terms of the phases, we also have different echoes here, there are different volumes. And again, the phase becomes a little bit more wrapped as the echoes are longer, you can see here. So this is the data that we've been using. And the first thing that we need to do is to find a mask for our data. And this will be important for later. Usually I like to use FSL bet command, because it's more useful, it's easier. You can script this for sure, but now I'm going to use the GUI, and I'm just going to use the bet. I usually use it, the threshold for the intensity, I use it lower, and this is because on when you calculate QSM maps, the actual filtering and whatnot will use the sort of an eroded mask. So you won't be obtaining QSM values for within the mask, but from an eroded mask. So I suggest to use quite a generous thresholding to include the more brain you can. Okay, and I just upload the magnitude data. This will mask actually the first echo, and it's actually really good that it masks the first echo, because you can see that you have more signal in this first echo than in the last echo. And if you just calculate this, you can see that when it finishes, I can upload it, and if I just add the mask that was just now calculated, it includes quite a generous amount of brain. I can flip back and forward. If I go to the fifth echo, maybe I can, and if I just load it here, you can, no, FSL doesn't really allow it, but you can see that the brain is much smaller, let's say, because there isn't much signal on the last echo remaining. Okay, cool. So now we have the mask, and now we need to do another thing before we actually start calculating maps. We need to scale our phase data, because our phase is actually from 0 to 0.04096 integer. This is how data is scaled on a Siemens scanner, which is the scanner that we have in Cambridge. So we have to scale it usually between software packages like it between -pi to pi, including STISuite. So what I usually do is I just use FSL commands. So in this case, I'll just put this here in the center. I use FSL maths, and I have my raw phase, and I just subtract half of 4096, which is 2048, and I just give it a temporary window image, and I use again FSL maths on this temp data, and I divide it by 2048, multiply it by 3.1459, which is approximate, and then I can call this phase of phase range coral. This will be a phase, your phase data with, and you can check this by using FSL stats. Range corrected, I think it's R, which gives you the limits, and you can see that is more or less between minus 3.14 and 3.14, minus pi to pi. Great, so now we have prepared our data. Now we can load STISuite. You can load the STISuite package from the STI website, and once you do that, you can, and this is a package that's compatible with MATLAB. So what I usually do is I load MATLAB and on HPHI, and because this is HPHI, it will not save any of your directories, so you have to load into the actual path for STISuite, which you will do it in a second once this is open. So you have to set a path of the STISuite. I have saved it in my home directory, and you can put it wherever you want. MATLAB folder here. I just put STISuite 3, which is the version I'm using, and then what I should have done is actually add with subfolders, because this is quite important. Let's just do that again. MATLAB STISuite open, and so all of the folders are added. I close, and that's it. So now if I write STISuite, so sort of the GUI appears, and this is sort of your GUI. You can also script this and make it as a pipeline for your analysis. And if you click on command line templates, this is sort of the STI templates that they have generated. You can see coil combination functions, read icons, phase unwrapping, V-sharp filtering, and Harparella, which is other methods, or the Harparella methods, the ILS QR and STI methods, the star QSM, etc. But what we want is actually just to look into the pipeline and the GUI pattern. So I just clicked QSM GUI, and another window will appear at some point. Okay. Great. So this is sort of what you can use. And the first thing, because it's a GUI, it has quite a few bugs. The first thing you need to do is actually set your parameters here. So, and I suspect this is because we load Nifty data, but I have not tried loading DICOM data. You are welcome to try this as well. So the first thing I do is I load I set the B0 field, which is 7 Tesla, and I set the T1, which is the first echo of your the first echo time that you have. It depends on your protocol. In my case, it was 4068. You can set your delta T, which is the difference between your first and your second echo, for example. And in this case, mine was 3.24 milliseconds, and this is all in milliseconds. And the sum T is the sum of all your echo times. And if you sum them all up, in my case, it's 76.68. And that's it. Don't worry about the voxel size, because this will be uploaded directly with your Nifty, when you upload your Nifty data. So I just click the magnitude, and I just load the magnitude, the raw data. So I just load that there. to wait a bit until it says loaded something here, and the image will appear here on the left. I'll just wait a little bit. Okay, and then you can load your phase data by clicking here. In this case, you're wanting to load your range corrected data, so you load phase range core. And you can see here that the voxel size has been changed from 111, which was the default, to 0.7. In terms of your H vector, you don't need to worry about this because we always acquire our data transverse, and your B0 will always be pointing in the Z direction, positive, so this will always be 0, 0, 1 vector. Cool, so now step 1 and step 2 are done, so now we go into the next tab, which is the QSM tab. Do not click on this single button for QSM because this does not require any additional probably parameters that you actually need to change. One things for sure is the masking. You can use their own thresholding method, which I do not advise. I advise actually to load your own mask, and as I've done in the beginning, I've done masking with FSL, and I reckon this is quite a good one, so I just load this one here. And yeah, you can see here that the mask has loaded, and then you can pass on to the step 4, and this is related to processing your face. So now it's actually doing some steps that will create your QSM map. So if you click on, because we acquire data in 3D with 3D GRE scans, you click on 3D GRE data. In case it's otherwise, I will tell you why. In terms of the radius, I just use the default for now, but you can play around with these parameters a bit and see what it will influence on your data. So I'll just use this and I'll click here. It will start with phase unwrapping, as you can see here, and it will unwrap all of your echoes. So in my case I have 6 echoes, so it will start with 1 and it will finish up with 6. And this is a process that will take a little longer, perhaps probably 2 or 3 minutes, but we'll just wait until it finishes. You can only proceed once it says done here or something, filtering done. So do not click on anything else before it has finished whatever process it is doing. Notice as well that there are some variables saved in your workspace. Here there are the variables that you have uploaded, the magnitude, the mask, and the phase, and others will be here appearing, especially, for example, the filter phase. So you see that it had done the phase unwrapping, now it's doing the filtering with this V-sharp method, and it finished, so in more or less 10 seconds. And it said V-sharp done, so now we can proceed forward, and we saved some of the variables there. So in step 5, which is the QSM or the inversion part, you have 2 alternative methods. You can either do the star QSM method or the ILSQR method. The star QSM is much faster, although I would say it's more niche and less precise. The ILSQR method does take longer, but it's more well known, and I would recommend to use this one here. So in this case, I'll just click on it, and then we'll just wait for what happens. It says starting QSM processing, please wait, and it says running ILSQR method step 1. It has 2 steps, and you just have to wait until it finishes. And then after this finishes, we will run as well star QSM, but let's wait for this to finish. Okay, so now it's nearly done. You see that it has started on step 2 and then sort of reached its last iteration. It says done, took 214 seconds, and now we were sent to the visualize tab. In the visualize tab you have two left and right images. Because this has bugs, the first image is not what you see in here, but on the left image it will appear whatever you click here on this left column, and on the right image here it will appear whatever it is on the right. So if I have on the left magnitude, it appears the magnitude, also the face, just the raw face, the mask, the Laplacian, this is the filtered face, in radians, and then the frequency just converted, and I can also upload the star QSM, the ILS QR, QSM maps in ppm, and this is sort of what you want to save. You can save in dicom.mat, but usually I save it in Nifty format, and I just save it in my current folder. Okay. I can also save the magnitude, which is also quite useful to save it, because this is magnitude combined. You can save the mask, but you actually have this, and you can also save the phase. Usually people like the frequency shift, so I also save this. And okay, and this is it. So if you go back to your folder, you can see that these are the images that you saved. As I said, you can also calculate the QSM maps using the star QSM method, and I will just run this very quickly and to see what happens. You see that in your command line it says performing star QSM and says initialization, and it will take much less time in this case to compute the maps. And just wait a second, then you'll see what are the differences. So starting solver, and yeah. Wait a second. Okay, and this is the other alternative QSM maps. It takes, you see, much less time, and if you just put them side by side, so here would be the QSM with the ILS QR method, and here the QSM with star QSM method. You can see the differences, and one is much sort of brighter here than this, and these are actual artifacts due to be not homogeneity near the sinuses, and here near the ear canals and stuff. So you can see that the ILS QR method is probably the more preferable one, although it does take longer. You can see if I set this in as Nifty as well in your current folder, and if I upload this just in FSL Maths, or FSL View, sorry, you can see the differences better in this 3D view plane. Usually I like to scale it between minus 0.1 ppm to 0.1 ppm, so sort of you find it that this is the ILS QR method. Looks pretty good. If I just load this QSM star method, and I add the same type of range, and I put sort of the cursor more or less here, you can see the difference. There are quite remarkable differences between both, and one is sort of less susceptible to these artifacts than the other. There are of course alternative ways to calculate these maps, but in STISuite they just make these two available, and it's really great. Okay, and this is it. I hope this was useful. Thank you.